So we want to start talking about a very important type of continuous random variable called a normal random variable. All right, and it is, if you've ever heard the term the bell curves, that's what a normal random variable is. It has to do with the bell curves. And so one important thing, this is true for most continuous random variables. Whenever we say x is normal, it's defined by its mean and its standard deviation. So just a rough picture of what it looks like. I'm going to show you a more specific one in a minute that comes from the textbook. But we basically have this bell curve shape. It's mounted up around its mean. And so you got to remember always, whenever you're talking about a continuous random variable, the x-axis gives the values of your random variable, and the function gives you the PDF, so basically the probabilities. So it's mounted up around its mean, and then it tapers off to the left and right. And the standard deviation plays an important role. It tells you how spread out that data is. And so you could have a bell curve that just peaks really sharply around the mean. That's in the case where the standard deviation is small. Or you could have a normal variable that is very long and flat, and that is the situation where the standard deviation is large. Now, a couple basic things about the normal, coming back to this first picture here before I show you a more specific picture. You got to look at it carefully, but there's an inflection point on that PDF right there, and that's always at the standard deviation. So the point of inflection happens at a 1 standard deviation range. It's not really important for discussing statistics, but just to start giving you an idea about how that standard deviation affects the spread. On this skinnier one here, the standard deviation would be really close to the mean. On this flatter one over here, the standard deviation would be right out here, and so that spreads out the data set. So I made this slide once, but I realize your book is using some somewhat non-standard notation. It just depends on what book you're reading in. So it's kind of frustrating to me. But anyway, we'll see this notation right here. X with the tilde, and it'll say n, and these two numbers will be given to you right here, the mu and the sigma squared. So the way your book is defining and what that notation means is it's saying that x is distributed. That's the way you read that tilde as a normal variable with mean mu and variance sigma squared. So this is the part that I'm frustrated by. A lot of books and people will specify the standard deviation. So just be careful of that in the book whenever you're doing problems. All right, so it's going to define a normal random variable by its mean and its standard deviation, or by its variance. See, I got caught because I'm used to using standard deviation right there. So be aware that it's going to give you the variance in the book. All right, make sure you realize those are two numbers that you'll be given. All right, so it might say like 50 and 9. Okay, and so that would mean that the mean is 50, the variance is 9, and that would tell you that the standard deviation is 3. Okay, so what that notation means is that, like I said, x is a normal random variable, and its mean is going to be mu, and its standard deviation will be sigma. All right, now let me show you a picture about what that means in terms of probabilities and the spread of the data. So here's a picture of a regular bell curve. So right in the middle of the mound is the mean. So mu is right here. Like I said, I was showing you a geometric property, but that point of inflection happens in the 1 standard deviation range, and right about 68% of the data land within 1 standard deviation of the mean. Always remember, whenever you're seeing this kind of graph, over on the x-axis is the values of your variable, and then how high that PDF is gives you the probabilities. Okay, and so this is saying that 68% of the data for a normal random variable lands within 1 standard deviation of the mean. And then if I look at the 2 standard deviation range, about 95% of the occurrences occur within 2 standard deviations of the range. And If I look at 3 standard deviation range, about 99.7% of the data land in that range. Okay, so theoretically, whenever you have a normal random variable like that, it can actually take values between negative infinity and infinity, theoretically. But you can see from that 99.7, it almost always lands within 3 standard deviations of the mean. So it kind of has this range here from mu minus 3 sigma to mu plus 3 sigma. At least 99.7% of the time it lands within that range. All right. But there is this small theoretical chance that a normal random variable can land outside of that range. Now remember, to compute probabilities, we need the PDF, the probability density function for a continuous variable. And so if we say that x is normally distributed with mean mu and variance sigma squared, then we need to know what its PDF is. This is its PDF. It is a very strange PDF. To be able to get that bell shape, we start with this exponential function. And then just like that problem on the test where you needed to find the value of c that made a PDF, you integrate this thing from negative infinity to infinity. If I did that without the constant out front, this comes out to be sigma times the square root of 2 pi. And so then to get it to be a probability density function, we divide by that number. So that's where that constant out front comes from. I know it's a strange PDF, but that's what we have to deal with. And so remember, the relevance of that is if I want to compute the probability that my normal variable is between two numbers like that, then I'm trying to find the area under the PDF like that. And so to do that, I integrate my PDF between my two numbers. And so I do the integral from a to b of my f of x dx. And the f of x that I need to work with is this function right here. And so that's one way to start getting to probabilities, is to use this function. I will tell you, it's such a common thing. There's usually other either calculator or software functions that'll compute this integral without having to type in the integral. But one way to do probabilities is to type this thing in, and then whenever you need to do a probability is you just do the integral of that function. One thing about this to mention too is that f of x has, this is a typical example I use in Calculus 2 class, this has no closed form antiderivative. And so don't worry too much about that. The thing is I noticed on the test, especially some of you were trying to do all those integrals by hand. You ate up a lot of time. You didn't need to do that. I told you you could use your numerical integrator to do those kind of integrations. And the thing is, you can't do these by hand. There's not a function that we can say is the antiderivative of our f of x up here. And so if you're going to use, if you're going to try to integrate this function to do probabilities, you have to use your numerical integrator. So let's try to get a specific example so this doesn't seem so abstract. So here's my notation. What is that saying? That's saying that x is normally distributed, and then the mean goes first and the standard deviation goes second. So that's telling me that my mean is 100 and my standard deviation is the square root of 25, which is 5. Now don't feel like you have to draw this picture out. I'm just want to show you what that more general picture meant a minute ago. So that means this bell curve is centered around 100. And then if we look at 3 standard deviations, that's 15, right? So if I go out here to 115, I just added 3 standard deviations, and then I come down here to 85. That's subtracting 3 standard deviations from the mean. And so what that means is that PDF is basically 0 there, and then it's mounted up around 100. Your pictures don't have to be perfect, and then it's practically 0 down at 115. There is a little bit of stuff left over here. So that's a very rough picture about what that bell curve looks like, okay, or that PDF looks like. All right, now say I told you to find the probability that x is between 101 and 90. Okay, like that. So here's where you just got to decide which calculator features you're going to use. But the idea is this is the integral from 90 to 101 of our PDF, f of x dx. And what is our f of x? It's 1 over sigma, which is 5, the square root of 2 pi, e to the negative x minus mu, that's 100, squared, divided by 2 sigma squared, which would be 25. And so I'd replace that 2 times 25 with 50. And so now make sure you realize this part right here is all in the exponent. Okay, so one way to do this problem is to use your numerical calculator to do the integral from 90 to 101 of all of this stuff right here, dx. But you can see that's pretty complicated to type in. You can do them that way. There's going to be other problems where you can't work directly with the function anyway. So as I'm talking, I'm realizing you might want to use these calculator features that I'm going to mention. If you don't use a calculator to do it, I know Excel has features that do the same kind of thing. You'll just have to look at some help pages or some syntax help for those to get those. And other software programs will include them as well.
I'm going to show you how to do this on a TI-84 calculator, but it's going to depend on your calculator. The key thing we're looking for, it's going to seem like, based off what we were talking about, I was talking about the normal PDF showing you what it is, but we really need the normal cumulative distribution function. If you use PDF features, all it'll do is give you the function value. It won't give you areas. And so on the TI-84 calculator, and all the TI calculators in general, you're looking for its distribution menu. And so notice right here it says DISTR, and so that's the key that we're looking for. And so I would just hit that, and notice right here at the very top it says normal PDF. We do not want to use the PDF. We want to use the CDF feature on the calculator. Alright? And so you might want to look too, since I have this menu up, we're also going to use this number 3 quite a bit. It's an important key. I'll explain later what it's for, but in general, we're going to need that key. So if you have an older calculator and you don't have that key, you might want to try to get your hands on one or look around on Excel about how to do this same thing. Okay? So anyway, I select normal CDF. If you're computing probabilities, you need to use that CDF. And so you hit that. And so what are we doing probabilities between? I already forgot. We're doing the probabilities between 90 and 101. So my lower bound is 90. My upper bound is 101. And then see, it's asking me for what my mu and my sigma are. Be careful. Remember, sigma is the square root of that variance. So don't type in the 25 there. Type in the 5. That's why I'm a little frustrated with the book. Okay? Then you hit paste. And so, especially if you have an older calculator, notice the syntax. If it didn't give you a menu, just type this and add a parenthesis. So you type the mean, the lower bound of your probability, the upper bound of your probability, the mean, and the standard deviation. Like that. But then you hit enter, and there's your probability.
Okay, and then make sure you realize what that's given you. That's given you that the probability that x is between 90 and 101 is about 55.7%. All right, so let's look at some more problems with this same normal random variable. And there is one little quirk we got to keep up with. So here's a problem like was on the test. And so the probability that x is within 2.5 standard deviations of its mean. And so remember what that means, that mu is 100, sigma is equal to 5, 2.5 times sigma is, I should know that, but is 12.5, like that. And so we're doing the probability that x is from 87.5 up to 112.5. And so in the bigger picture, you would be integrating your PDF between those two numbers. But we can use our cumulative distribution function feature, and I'm just typing the entry key on my calculator to bring that last line, since I have the same mean and standard deviation. You don't have to do that though. You can just go through the whole process again. And so I just type in normal CDF, 87.5 is my lower bound, comma, 112.5 is my upper bound, and then my mean is 100, and my standard deviation is 5. And try that out. Pause it real quick and see if you can get the same answer as I do. Make sure you have the basics about how to get these probabilities. But you go through and compute that, and you get about 98.8%. Okay? So hopefully you got that. So now a related problem, but you got to be a little bit more careful on your calculator, is say I wanted to do the probability that x is less than 90. Okay? Now, again, too, sometimes it's good to diagram these out to make sure you draw the right pictures. But here's 100, here's 90, and I'm doing the probability that x is less than 90. So I'm finding this area right here, all right? And so that's what I'm trying to find. Make sure you realize, in terms of the PDF, this is the integral from negative infinity up to 90 of my PDF function, okay? Now, if I'm going to use that normal CDF function, so I have normal CDF on my calculator. The key thing is remember, this is the lower bound and then the upper bound and then mu and sigma. So the last three numbers are easy to know what to fill in. 5 and 100. My upper bound's 90. The thing is, I'm trying to type in negative infinity right here, but your calculator doesn't really have an idea about what infinity is. Even you folks that are using CAS calculators, I don't think it would give you an answer if you type negative infinity there. I'm not sure. So what you can do, the key thing is, remember the idea of being negative infinity is that it's just a really small number. Okay? So sometimes if I don't want to think, I'll just type in something really small, negative 1,000, something like that, or negative 10,000. So the thing is, your calculator is actually going to be doing this through a numerical method. It might even pause for a couple seconds doing this integral right here. And so you might want to do a little bit more thinking. Since the normal variable almost lands within 3 standard deviations, sometimes for that lower number, whenever it's negative infinity, I'll do like mu minus 5 sigma. I would at least make that number 5, if not 10 sigma. And so 10 sigma would be 50. My mu is 100. And so you can see, why don't you try typing in negative 1,000 first, and then type in just 50. You'll see, at least in most decimal places that we need, that'll work for you. So now I'm doing this. Why don't you pause it and make sure again that you get the same answer that I do. But I'm typing in normal CDF 50, comma 90, comma 100, comma 5, and I get I get 0.0227, 5, ... Remember, I usually like you to give to the 10th of a percent, so that would be about 2.3%. Okay, just to show you, I'm gonna show you if I used negative 1,000 instead. I can't show you, but I'm gonna type it in and tell you what it gives me. That, and even there, even using instead of using 50 as my lower bound, using negative 1,000, it still gives me 0.0227 500. Yeah, gives me basically the same number. Yeah, actually, to all the digits it displays to, it gives me the same number. So that's up to you. Just make sure whenever you need to fill in a number for negative infinity or positive infinity, make sure that number is well out of the range, well out of the 5 standard deviation range. So one more related to that. Say I want to do the probability that x is greater than 105. So again, try to get in the habit of using these pictures to help guide you about which way to integrate. And I'm thinking more of other stats classes that are more basic where they don't know how to integrate. So we might not need to rely so heavily on the pictures. To use that other feature, the inverse normal, it does help you to have the picture. So you might want to get in that habit, and that way you can kind of check yourself too. But the point is here that if we were doing this with integration, we'd be starting at 105 and going up to infinity of our function. Okay, like that. And so if we're going to use that normal CDF function, I'd have normal CDF. The lower bound's obvious, it's 105. The point is I want to go up to infinity, but the calculator can't work with infinity. So you could use that 5 standard deviation range if you wanted to. That's 25, so I would just say up to 125, like that. Or you could just make up a number that's well outside of the bounds. We could just as easily use like 200 or something like that. Or you could use 1,000, just something that's well outside the range of what that normal value would land at. And then our mean is 100 and our standard deviation is 5. So I just need to do my normal CDF. Again, since I'm going to take a second to type it in, you may want to pause, make sure you can get it. All right, but 105 up to 200. And that gives me, as a decimal with most of the digits written, 0.158655. But rounding that to the nearest tenth of a percent, I get 15.9%. All right, so I hope that showed you how to do basic probabilities with the normal variable. We've got one small thing to talk about. All right, a special case of the normal variable is what we call the standard normal variable. And whenever you see this notation z, that's special notation for the standard normal variable. And what the standard normal variable is, remember this is mean and this is sigma squared. And so the mean of the standard normal is 0. The standard deviation is the square root of 1, which is 1. So this is a normal variable that's centered at the y-axis. And then, our 3 standard deviation range would be from -3 to 3. And so that normal variable roughly looks like that. I know my pictures aren't very good like that. What ends up happening in the bigger picture, basically everything that you can answer about a normal random variable is answerable in terms of the standard normal random variable. And there's a basic formula that translates between them. If you're starting with a or if you're starting with a normal variable, then x is equal to mu plus sigma z. And solving this equation for z, this is x minus mu divided by sigma. And this is an important quantity in statistics. It's called a z-score. And so what that does, that connects the two variables. And so you can answer any question about a normal random variable in terms of the standard normal variable. That's not going to be really important right now as we get started, but it's going to be really important later, especially whenever we use that other feature I talked about, the inverse normal. Some inverse normal functions only give you these numbers. And so then if you want to go back to your x variable, you use this formula to get that. We'll worry about that later, but the main thing is I want to point out the standard normal has mean 0 and standard deviation 1. So you might see a problem like this. Find the probability that z is between negative 1.5. Z is between negative 1.5 and positive 1.5. Like that. And so for your normal CDF, you would just type in normal CDF, and your lower bound is negative 1.5, your upper bound is 1.5, your mean is 0, and your standard deviation is 1. You would type that in and get the answer. I'm going to save us some time, but that's the way you handle that. So just remember, it might not. If you see a problem and it talks about the standard normal, it probably won't tell you this part right here. It'll just tell you you have the standard normal variable z, and then it'll go to start asking you probabilities. The key thing is to know that for the standard normal, the mean is 0 and the standard deviation is 1.